In this talk, I'll discuss our work Reproducibility in Learning. This is joint work with my advisor Russell Impagliazzo, Tony Pitassi, and Jessica Sorrell. We were originally motivated by reproducibility issues with the scientific method. Ideally, we'd like researchers to come up with hypotheses, test these hypotheses, analyze data, and report their conclusions. However, their conclusions aren't very meaningful if they cannot be replicated or reproduced by other researchers. In the past decade or so, there's been an increased interest in looking at reproducibility issues across science. In this Nature 2016 study, scientists in a variety of disciplines such as chemistry, biology, physics, medicine, and earth and environmental science noted issues either reproducing their own or someone else's work. This issue affects computer science as well. If we expend a lot of energy training a very sophisticated learning model, and if this learning model doesn't happen to be reproducible or it cannot be used in other contexts, then this model has very limited utility. To try to alleviate some of these issues, the community has banded together, in part by forming reproducibility workshops in which researchers are encouraged to either attempt to reproduce their own work or someone else's work, or in general just share best practices for reproducibility. When we think about possible issues leading to reproducibility issues, there may be many possible facets to consider. Of course, there could be some sort of active misrepresentation or malice involved, but there might be more subtle issues such as the algorithm's code or hyperparameters are not precisely communicated. There might be differences in the specific hardware, computational power, and precision of these devices. And there might be data ownership concerns where private data cannot be shared with other parties. Of course, there also could be issues with samples being unrepresentative or algorithms being very brittle when given slightly different samples and outputting widely different results. Our definition is mainly going to focus on this last possible issue. In our work, we give a new algorithmic notion of reproducibility, and we show how this notion can be applied to a variety of learning tasks, such as computing statistical queries, finding the heavy hitters of a distribution, computing an approximate median, computing a half space under a large margin assumption, and designing reproducible boosting algorithms. We also delve a bit into the properties and trade-offs of our notion of reproducibility. And this is our notion. Let distribution D be over universe X, and let samples S1 and S2 be drawn according to this distribution. And say we have some random binary string R also referring to the internal randomness of the algorithm. We'll say that an algorithm is row reproducible if, for all distributions D over the domain, the probability that the algorithm's output on the first sample using the internal randomness is exactly the same as the output of the algorithm on the second sample using the same internal randomness is high with probability at least 1 minus rho. This definition is inspired by work in pseudo-deterministic algorithms introduced by Gatt and Goldwasser in 2011, as well as techniques from works by Grossman, Liu, and Goldreich. A related notion is global stability introduced by Bunn, Livni, and Moran, as well as its generalization, pseudo-global stability, introduced independently by Ghazi, Kumar, and Manarangsi. It happens to be that reproducibility and pseudo-global stability are equivalent up to some transformation factors. Let's think about some of the simplest reproducible algorithms possible. What is a simple zero reproducible algorithm? Well, any algorithm that outputs a constant is perfectly reproducible as it does not depend on the samples or the internal randomness, but it's perhaps not a very useful algorithm. What's a simple non-constant zero reproducible algorithm? Well, an algorithm that outputs the shared internal randomness is not constant, but is perfectly reproducible as a reproducible algorithm is allowed to use this shared randomness to come to a sort of response. To reiterate, our notion of row reproducibility is an algorithmic property and should hold for all distributions. We leave the output type of the algorithm unspecified so that we can consider reproducibility in a variety of learning contexts. Again, there is a shared randomness R, and if it happens to be the case that rho is less than a half, then we'll see that many R's must have a sort of canonical representative for that particular R. I'd like to pause for a brief moment to talk about some terminology, specifically reproducible versus replicable. When we initially introduced this work, we were under the presumption that these two terms were used interchangeably. However, the most recent ACM categorization, updated in 2020, most closely aligns the word replicability with our definition. Next, we'll talk about reproducible statistical queries. We'll see how the shared randomness precisely allows us to decide on a canonical representative to return. In this problem, we're given sample access to a distribution and asked to reproducibly compute the expectation of a real valued function on the distribution within some tolerance tau. If we aren't worried about reproducibility, one thing we could do is we could just draw some examples and then take an average. As long as we draw enough examples by concentration bounds, we can guarantee that we'll be within the tolerance tau with high probability. Of course, this doesn't quite work reproducibly, because an algorithm that draws two separate samples can get slightly different results for the empirical averages. One way we might consider making this procedure reproducible is by rounding. So we can, if we draw some examples and take an average, if we round to the nearest integer, then as long as the confidence interval around our average is, or around the true value is small, then the empirical averages will be rounded with high probability to the same point. However, this strategy breaks apart when the true expectation of f of x happens to be close to one of our rounding boundaries. In this particular case, we're going to have to increase the sample complexity proportional to the distance between the expectation of f of x and the rounding boundary in order to guarantee that we're always going to, or we're going to with high probability, land on one side of the rounding boundary. That is, naively, this strategy makes it unlikely for two runs to output the same integer if these two values, again, the rounding boundary and the expectation, are close. So here's where our shared randomness can come in. Rather than having a fixed rounding boundary, we'll do randomized rounding. Again, we're going to draw some examples and take an empirical average. But afterwards, we're going to choose a random offset, alpha off, to move the boundary. This way, we can avoid this sort of worst case situation with high probability. So what we're going to have to do is we're going to have to take more examples such that our concentration bounds for the averages are tighter. But as long as the ratio between the width of the concentration bound and the interval size alpha is small, we can guarantee reproducibility. That is, we have a reproducible statistical query algorithm that draws roughly 1 over tau squared, 1 over rho minus 2 delta squared samples, and rho reproducibly computes a statistical query to tolerance tau. Again, our tolerance is going to take a hit because we do some randomized rounding, but as long as we guarantee that the confidence interval is small relative to the possible choices for the randomized rounding boundary, then we can guarantee reproducibility with high probability. In addition, in our work, we show a almost matching lower bound for statistical query algorithms. That is, there is a statistical query such that a rho reproducible algorithm with tolerance tau must have sample complexity omega 1 over tau squared rho squared. So some takeaways from this problem. Randomized rounding allowed us to reduce a possibly infinite feasible return space into a single canonical representative for each random string. Concentration bounds here allowed us to do randomized rounding as long as, again, we ensured that the concentration bound is smaller than the randomized rounding width. And we saw how the shared randomness helped us avoid these sorts of worst case situations where we might be near boundaries. This reproducible statistical query algorithm shows that problems solvable using just statistical queries are contained in the set of problems solvable reproducibly. And we'll see from the approximate heavy hitters problem that this inclusion is strict. Specifically, a heavy hitter of a distribution is an element in the distribution that has probability mass greater than V. So for a V heavy hitter. Let's define the set L sub V to be the set of V heavy hitters of D. The approximate heavy hitters problem asks us to output a set that includes all the V plus epsilon heavy hitters and includes maybe some of the V minus epsilon heavy hitters. So we give an algorithm for the approximate heavy hitters problem that has a sample complexity that does not depend on the domain size. But we also show that any algorithm that relies solely on statistical queries for the approximate heavy hitters problem requires a number of queries that has a logarithmic dependence on the domain size. Therefore, the inclusion is strict. Moving on to approximate medians, let's say we have a distribution D over a well-ordered domain X. An element is a tau approximate median of this distribution D if it happens to be the case that this element is within a tau probability mass of the true median. And again, we're requiring our domain to be well ordered. So we design a reproducible algorithm R median with techniques inspired by prior work on differentially private interior point. And the algorithmic idea is roughly as follows. For simplicity, consider the domain being 0, 1 to the D, and consider running a non-reproducible median algorithm twice. So if this algorithm is accurate, then it's likely to be the case that the shared prefix of the result of these two algorithms is a prefix of a true approximate median. So we look for likely lengths of the shared prefix, and once we've picked a likely length, we can search for that common prefix and recurse. This gives us a row reproducible algorithm for the approximate median problem that has an exponential in the log star of the domain size dependence for a sample complexity. Combining prior work on differentially private approximate medians, lower bounds, and work on pseudo-global stability, we get a there is a sample complexity lower bound of omega log star of the domain size. Another interesting corollary of our reproducible median algorithm is this idea of combining reproducibility with correctness via composition. Specifically, if we have some problem where the correct answers form an interval, and we have a good but non-reproducible algorithm for that problem, we can do a composition R median composed with that algorithm to get a reproducible algorithm for the original problem. That is, we can get correctness almost entirely from the non-reproducible algorithm, and we can get reproducibility from our reproducible algorithm. Next, I'd like to turn to pack learning. In Valiant's pack learning model, there's a concept class C and an unknown function f that we want to learn. And we're given sample access to labeled examples drawn from some distribution. We'd like to construct a pack learner, which is an algorithm that, for arbitrary epsilon and delta, gets misclassification error better than epsilon with high probability. The concept class we're interested in is half spaces in RD with a margin tau. And the way we're going to reproducibly learn half spaces is by reproducible weak learning and reproducible boosting. Specifically, we build on the reproducible weak learner introduced by Servidio's 03 work, and we find an interesting connection to Kindler, Rao, O'Donnell, and Wignerson's work on foams in order to get a reproducible half-space learner. For the boosting side, we again rely on Servidio's 03 learner, and we show how each individual step of that smooth boosting algorithm can be made reproducible. So some more preliminaries: a weak learner is an algorithm that does not have to get arbitrarily good misclassification error epsilon, but just has to do better than a half, better than random guessing. So we say the amount better than a half gamma is the advantage of the weak learner. And a boosting algorithm is a generic black box way to convert weak learners into strong or pack learners for the same problem. So specifically, Servidio's half-space weak learner works by drawing a sample and then computing a weighted average of the vectors drawn. Then this is normalized and returned as a hypothesis. They show that the advantage of this hypothesis return is proportional to tau, the margin. However, this is not a very reproducible way to compute a half-space, as any individual vector can perturb the resulting half-space. So here we turn to this work on foams as a way of doing randomized rounding in higher dimensions. Specifically, within this work, the authors give a randomized algorithm for generating a tiling of the space Rd. This tiling naturally induces a mapping of Rd to nearby lattice points. One exciting property of this work is that the probability that 2 points are rounded to nearby lattice points can be bounded by their L2 distance times a constant. So, similar to the statistical queries example, but in a higher dimension, as long as we have a sort of vector concentration bound, we can combine it with this randomized rounding scheme, with this Foams construction to get a randomized rounding scheme, again, in higher dimensions. Specifically, our weak half-space learner is reproducible by first computing, again, the same statistic, this weighted empirical average, using the shared randomness to generate a tiling, and then using the tiling to round our resulting empirical half-space vector to a nearby point. And we showed that our half-space weak learner row reproducibly returns a hypothesis with advantage proportional to the margin. Next, turning to the boosting side, we build on the smooth boosting algorithm introduced by Servideo. And this boosting algorithm in particular has many individual steps that can be made reproducible. For example, the initialization is deterministic. The number of times this boosting algorithm calls the weak learner is determined by statistical queries, and these statistical queries can be made reproducible. The weak learner call itself is reproducible by the previous slides. And the reweighting of the distribution as well as the final classifier output are deterministic. In combination with the result, an adaptivity result showing that essentially we can union bound over losses in reproducibility, we get a boosting algorithm that is overall reproducible. Combining with our reproducible half-space learner, we get a half-space strong learner that's both reproducible and has sample complexity polynomial in the dimension, 1 over the margin, 1 over the accuracy, and 1 over the reproducibility. However, this particular construction runs in expected exponential time because the Foams construction runs in expected exponential time. So in our work, we give an alternative rounding scheme that has a worse dependence on sample complexity but can be efficiently executed, thereby giving us a reproducible half-space learner that runs in polynomial time. To summarize, we give a new algorithmic notion of reproducibility, and we show how to make some of the standard and natural learning tasks reproducible, such as computing statistical queries, finding heavy hitters of a distribution, computing approximate medians, and finding half spaces under a large margin assumption with boosting algorithms. In addition, we talk about some of the other properties and trade-offs of reproducibility in our paper. Finally, I'd like to mention some recent developments relating reproducible pack learning and approximate differential pack learning. That is, connections between reproducibility, pseudo-global stability, Littlestone dimension, and approximate DP pack learning give sample-efficient reductions between reproducible pack learning and approximate DP pack learning. So in terms of future directions, we're interested in understanding more about the connections between reproducibility and differential privacy, especially in other models beyond the pack learning and supervised learning models. We're also interested in going back to the original motivations for this work, seeing if we can adapt some of our ideas and techniques for better reproducible and replicable science. In particular, one thing we're thinking about is making hypothesis testing row reproducible. We're also considering expanding our definition to better handle distributional shifts, that is, when one sample comes from one distribution and another sample might come from a related but not quite identical different distribution. And with that, I'd like to say thanks for listening to my talk. I'd be happy to discuss these ideas further either at STOC or via email. Thanks again.